Welcome back to session 16 on combined loadings. We're going to get into the third portion of our session, focusing on the superposition of shear loads, okay, or shear stresses. And in this case, we're going to be looking at systems that look kind of like this one, where maybe the force itself is not a torque, okay, but it's applying a torque to a system, or it's applying a shear, it's creating an internal shear force to the system that results in a shear stress, okay, which is actually what's happening here. We have an average shear stress that results in a transverse shear stress, and we also have a torsional or torque that's being induced onto this shaft that's causing a shear stress. Okay, so this is the same procedure. Now we've seen it twice. Okay, section the material, determine the normal and shear force components at that section, determine normal and shear stresses at that section. And in this case, we're looking at shear stresses, okay, for this portion. And then we add the normal components to each other, or the normal stresses, and add the shear stresses together. So in this portion, we're looking at adding some shear stresses to each other. What are the possible sources of shear stress? Well, we have discussed previously how we can look at shear stress because of transverse loading, and we described transverse shear stress, okay, with tau is equal to VQ over IT. We've also looked at the resulting shear stress from a torque being applied to a shaft, and we know that that can be given as torque times rho over J. Now, going back to average or shear force that we can think of as having some average shear stress on a surface in a beam, we can save ourselves a lot of time if we remember a couple of equations that we derived back when we were looking at transverse shear stress. And this is the less common situation where we'd have a rectangular cross section for combined loading. Often we're looking at circular shafts because we're not, we haven't described how to put a rectangular shaft. You can look in Hibbler's book, you can look at other sources, there are correction factors and things of that nature. But for this semester, we're not gonna cover that twisting of a rectangular cross section or a shaft with a rectangular cross section. So this one may be less used, not because it's not valid. Okay, we can calculate, this is a very valid formula for calculating a transverse shear stress on a rectangular cross section, but often would combine loading. Since there's the twisting of the beam or the shaft itself, we are looking at circular cross sections. Okay? And so this formula is the one that can save you a lot of time. If we have a cross section and there's a transverse shear stress, okay, being applied to this face, okay, and we're on the neutral axis, the maximum is going to be 4/3 tau av, right? So we can figure out what the average shear stress would be by looking at the V dividing by the cross-sectional area. So here's the V, and then we figure out what the cross-sectional area is, and then right here it's just 4/3 times that average. It's a very useful equation. It saves a lot of time, and will save us quite a bit of time as we do some examples here. So here's an example. We have a circular beam or shaft with the configuration as shown, and this is blown up from what you saw on that introductory slide a few minutes ago, and actually at the beginning of part one. But now we're going to tackle the problem itself. So here is a shaft with a bend in it, okay? And yes, my drawing is not the greatest, but this is a right angle bend, and we see that there's a P being applied upward here at the end at a distance A from the bend, okay? And that is going to induce some twisting, right? So this portion is going to want to go up. It's going to whoop like that, right? It's going to be essentially like us applying a torque. We could call it T-gap, right? In the positive X direction with magnitude of PA, all right? P times A. This P, though, can also be transported over to here, right? And that's like having a force P acting along this beam, which would be causing an internal shear force, which would give us a shear stress at this location A, right? Because there's a shear force, and then we can think of it as an average shear stress acting on this face, and this is on the neutral axis, okay? And so it's going to be hitting a maximum. So that's where that 4/3 tau half is going to be becoming useful in a few minutes. So here's another perspective. Looking at the cross section, here's point A. X is coming out of the board. Y is positive. Okay, and drawing it yet again, we can have our A here, and there's Y, and X is coming out. Now, we want to break this into two problems, essentially. We want to think about transverse shear stress, and we also want to talk about twisting. Let's take a look at transverse shear stress first. So, transverse shear stress can be thought of having an internal shear force acting on this face that's magnitude P. Okay, and we've kind of skipped through a few different things here. Okay, but that is the direction that force would be acting, and so we can kind of simply say that the shear stress due to this P, okay, can be thought of as an average shear stress, right? We derived this previously, times 4/3 is going to be maximum at this neutral axis, and that's the contribution of P to a transverse shear stress. That's it, pretty much. Okay, right here, that's it. Now, let's look at what torsion is doing to the system. We have a shear stress from torsion, and we can write it as we see here as this PA, okay, and that's essentially causing that twisting that we've discussed, and that equation, or the equation that we use, is TC over J, just like we see here, okay, and the torque we said is PA already, so torque is equal to PA. C, right, is the radius. We've already used that here. And J is pi over 2, C to the fourth. And so now we can say that the shear stress, sorry, the shear stress from torsion, this tau T, is just the torque times C divided by J. Okay, and this is the resulting equation. 2PA over pi C cubed. Let's now begin to attempt to draw what the state of stress looks like. So this is stress due to torsion, okay? Like you see here, right? It maxes at an outer edge, and it's going circumferentially, right, around this face. And we also have a transverse shear stress, which is going to be acting upward, okay, and maximum at this neutral axis. So what do we do with these two shear stresses? It can be a little bit complicated to plot shear stresses on an element. Okay, so let's do it kind of what you might consider to be a little bit backwards, but safe. Okay, so here is an element that is drawn at A such that X is coming out the left side and Y is coming out the top. Okay, and Y is this vertical. So if I were to try to draw this element here, okay, it looks something like that. Okay, that's not the greatest drawing. Okay, but that's what the element looks like. Sorry, fan heater's turning on. So what would tau xy look like? to make things kind of go the direction we think they should. Well, in this case, look, there's a shear stress going up in both cases, and X is coming out of this side. So, okay, so I've got a positive Y. The question is, do I put it on the left side or on the right side? Well, X is coming out of the left side, so I'm going to put this shear stress to be positive on this left side. And this is tau xy. Wait, what does that mean? Remember, if we go back to our convention and our nomenclature, that the first component is the face, right, the x face, and the second component is the direction. That's the y. So tau xy is, in fact, upward in the y direction, in the positive y direction. And it's nice because that corresponds to what we see here as well. So now how do we draw the rest of the elements? Well, or the rest of the shear stresses on this element. We have a component that has to match this. We put head to head. And then these components are going to be drawn correctly, which is not. Okay, it should be drawn like this. Okay. And then if we want to think, okay, this looks negative. If you remember what we said before, like normally we want them going up to the right. Well, normally what happens is we have this flipped so that, you know, X is coming out the right side, not the left side. So if we flip, okay, what we have here, and I knew this was going to end up being wrong as soon as I saw it there, okay, that now we have these two meeting over here. This is positive X, this is positive Y. This is maybe a little bit confusing, all right? And to be honest, shear stresses, how do we put it? Direction doesn't matter so much as when we have compression and tension, but it does matter when we had to add and superpose them on top of each other. We need to make sure we know, are we adding two positives, you know, adding two shear stresses acting in the same direction, or is one acting in one direction and the other acting in the opposite direction? So it can be a little bit confusing, and it is important to be able to keep track of this. And even, you know, as you see, I made a boo-boo here. Okay, so what is tau xy? That's now the question. Well, tau xy, it's nice, right? It's going to be the superposition of these two, of the transverse, or the due to torsion, okay, stress due to torsion, the shear stress. That's like TC over J one. And the transverse shear stress, right? This is what we'll call tau V. So we can just add those two components to each other, and this is the resulting magnitude. And either this diagram or this diagram would be correct, okay, depending on how we do the X and Y. This is kind of the more conventional one, but this diagram corresponds more directly to what we have shown here with our coordinate system, okay? So for now, take some time and look at this question that I've created. We're going to determine the shear stress tau xz. at this location A. It's on the top of this this loaded cylinder, or this shaft, and there is a force P acting in the minus z direction, while a T-ap is acting in the positive x direction. Okay, and so this is an opportunity to look at superposition of shear stresses. Okay, enjoy and see you in the next portion.